Good morning, students. This is the last topic in solid state chapter, that is properties of solids. Here we should discuss two properties. They are electrical properties and magnetic properties. First we will discuss about electrical properties, then later we will discuss about magnetic properties. Electrical properties. Based on conductivity, the solids are classified into three types. What is conductor? If any substance is able to produce electricity, when we pass electricity through that substance is considered as conductor. We know that very well. Based on conductivity, these solids are classified into three types. They are conductors, semiconductors and insulators. If we discuss about these three, then this topic will be finished. First we will discuss about conductors. What is conductor? The conductivity range is 10 power 4 to 10 to the power of 7 ohm inverse meter inverse. That means these are the dimensions of conductivity. That means in that conductors, the conductivity range is very high. Why in conductivity range is very high in case of conductors? That will be explained based on band theory. Band theory. See, conductors, semiconductors, insulators. According to band theory, the conductivity of conductors is very high than semiconductors. The conductivity of semiconductors is very high than insulators. That means conductors conductivity is more than semiconductors than insulators. That means they have very less conductivity, or we can say that they don't exhibit conductivity. Why they don't exhibit conductivity? Why these exhibit more conductivity? That can be explained based on band theory. Listen carefully. According to band theory, BAND, according to band theory, every substance, every solid substance contains two bands. They are valency band and conduction band. What is valency band? That valency band contains valency electrons. These dots indicates what? Electrons. In case of conductors, this valency bond is overlaps with conduction band. So what? When this valency band overlaps with conduction band, when you apply electricity through this substance, then the electrons which are present in valency band easily jumps to conduction band. When those electrons easily jumps to conduction band, then that substance is able to produce conductivity. So that the conductivity of conductors is very high compared to these two substances. Why the conductivity of conductors is very high? According to band theory, the valency bond is overlaps with the conduction band in conductors. But in case of semiconductors, the gap between valency band and conduction band is somehow more. Here gap is there. So what? When we apply electricity, few electrons, not all electrons, few electrons only jumps to conduction band, so that these substances exhibit conductivity. These substances exhibit less conductivity compared to this one, because very few electrons only jumps to conduction band from valence band when you apply electricity. But in case of insulators, its gap is very high. Which gap? The gap between valence band and conduction band is very high. Even when you apply electricity, there is no chance to jump these electrons to conduction band. Then there is no chance of conductivity in insulators. So that insulators do not exhibit conductivity and conductors exhibit more conductivity. What is the reason? In this case, these two are overlapped with each other, or in other words, the gap is very less. But here gap is somehow more, so that conductivity is very less. Here gap is more, so that conductivity is very less. There is no chance to conduct conductivity by insulators. Here conductivity range is how much? 10 power 4 to 10 power 7 ohm inverse centimeter inverse. Here conductivity range is 10 power minus 6 to 10 to the power of 4 ohm inverse centimeter inverse. That means compared to this, here conductivity range is somehow less. Here conductivity range is 10 power minus 20 to 10 to the power minus 10. That means here values are negative. That means no chance to exhibit conductivity. Next point. when you increase temperature, in case of conductors, conductivity decreases because all conductors are metals. When you increase temperature, what happens? The resistance of the metal increases. What is resistance? Opposing force. The resistance of the metal increases. Whenever resistance increases, conductivity decreases. So in case of conductors, when you increase temperature, conductivity decreases. This is important point. But in case of semiconductors, when you increase temperature, some of the electrons can easily jump from valence band to conduction band. Automatically conductivity increases. So the conductivity of semiconductors increases when temperature increases. But here gap is more. Even if you apply more temperature, there is no chance of jumping electrons from valence band to conduction band. Then there is no chance of exhibiting conductivity. So temperature is independent. Here temperature is inversely relation with conductivity. Here temperature is directly proportional to conductivity. Here temperature is independent. So these are the properties, electrical properties of solids. Here some more points are there. We have to discuss some more points regarding semiconductors. Semiconductors are classified into two types. They are intrinsic semiconductors and extrinsic semiconductors. What is intrinsic? Intrinsic means pure silicon or germanium crystals are called intrinsic. That means if that silicon and germanium is not having any impurities, that is why those are called pure. If they have any impurities, if they don't have impurities, that is intrinsic. If they have impurities, they are extrinsic. Here we have to know one important definition. What is doping? Doping means addition of impurities to the given crystal. I repeat once again, addition of impurities to the given crystal is called doping. Why should we add impurities to the given system? To increase conductivity. To increase conductivity of the given crystal, we should add some impurities. That process is called doping. So that is important definition for 1 mark. The conductivity of semiconductors. The conductivity of semiconductors increases by adding impurities. Adding impurities is called doping. Generally we add 3A group elements or 5A group elements to silicon and germanium. This silicon and germanium comes under which group? 4th group. That means to the 4th group elements we add 3A and 5A group elements. Then only that 4th group elements exhibit conductivity. How they exhibit conductivity when we add these elements? Now we will have to discuss those points. See, in doping, two processes are there. One is N-type semiconductor and another one is P-type semiconductor. In other words, semiconductors are two types. They are N-type semiconductors and P-type semiconductor. What is N-type semiconductor? First I will show the silicon crystal. Silicon crystal is like this. See, this is the crystal of silicon. Between silicon bonds are present. Why these bonds are present? Due to attractions. See, the structure will be like this. Here what is the point? In case of N-type semiconductor, we add 5A group elements to 4A group elements. What are 4A group elements? Either silicon or germanium. Generally we take these two elements in 5A group. We have to add which one? 5A group elements, either phosphorus or arsenic atoms, to silicon crystal or germanium crystal. Then what happens? Then some of the silicon or germanium atoms are replaced by phosphorus or arsenic atoms. Whenever you add 5A group elements to 4A group elements, some of 4A group elements are replaced by 5A group elements. Not all atoms, very few elements. Then what happened? 5A group elements having valence electrons 5, 4A group elements having valence electrons 4. Between valence electrons, some attractions are occur, some attractions present. Due to that, some bonds are formed. Those bonds are called covalent bonds. After forming covalent bonds, here see, if you observe this structure, 4 bonds are formed. That means 4 valence electrons are involved from silicon atom, from phosphorus atom. But still phosphorus contains 1 valence electron, because it does not form bond with other atom, because the other atom does not contain valence electron. Then there is no chance to share that electron with other atom. Then there is no chance to form another bond. So whenever you add 5A group elements, then what happened? 1 electron will remain at 5A group element. That electron migrates towards the crystal. Whenever that electron migrates towards the crystal, then automatically that crystal exhibits more conductivity. That means the conductivity of the crystal increases. The conductivity of the semiconductor increases. That is called N-type semiconductor. Why we should say here that is N-type? Here N stands for negative charge. Here unpaired electrons are present. Electrons carries negative charge. So that we should call it as N-type. One more type is there, that is P-type. In this case, we add 3A group elements to silicon or germanium crystal. Here we add 5A group elements to silicon or germanium. Here 3A group elements to silicon or germanium. Here what happened? See, if pure silicon or germanium crystal is doped by boron or aluminum, then some of the silicon or germanium atoms are replaced by boron or aluminum, as like this. See, 3 electrons of boron or aluminum involves in bonding, correct? Because it contains only 3 valence electrons, while the 4th is electron vacancy or hole is formed. That means at aluminum 3 unpaired electrons are present. Those 3 unpaired electrons are involved in bonding. After that, electron vacancy is formed. That is nothing but hole is formed. This hole migrates towards the crystal. Due to that, conductivity increases. See, whenever a hole is formed at this aluminum, suppose here one valence electron is present at silicon. This valence electron occupies this hole. Then hole is formed here. To this hole, one more valence electron from another silicon atom occupies this position. Again, hole is formed at that atom. That means hole is migrates towards the crystal. In that process, electron also migrating. Whenever electron migrating, automatically conductivity increases. Like that, semiconductors conductivity increases. So here we have to remember 2 points. Here there is a chance of increasing conductivity of semiconductors by adding impurities. First chance is what? When you add 50A group elements to silicon or germanium crystal, then conductivity increases. That is called N-type semiconductor. P-type semiconductor means when we add 3A group elements to that silicon or germanium crystal, then also conductivity increases. So these are the 2 possible ways to increase the conductivity of the semiconductor. That process is called what, students? Doping. That process is called doping. This is all about electrical properties. In these electrical properties, these 2 topics are very important. Doping, types of doping, nothing but N-type semiconductor, P-type semiconductor. These 2 topics are very, very important. Now come to magnetic properties. We know some definitions already. Some more new definitions are there. If we discuss those definitions, then this topic will be finished automatically. This chapter will be finished. See, First definition, diamagnetic substances. What are diamagnetic substances? The substances which are repelled by external magnetic field is called diamagnetic substances. Example, NaCl, KCl. These are water. These are diamagnetic substances. Paramagnetic substances, the substances which are attracted by external magnetic field. That means when you apply magnetic field to the substance, that substance is attracted towards that magnetic field. That is called paramagnetic substances. We know these two definitions very well. Now another definition is there. What is that? For paramagnetic substances, VO2, Fe plus 3, Fe plus 2. These are the examples. Next, because it contains unpaired electrons. Ferromagnetic substances. These three definitions are new definitions. Ferromagnetic means the substances which are strongly attracted by external magnetic field. Strongly attracted. That means in case of paramagnetic, they are weakly attracted. But here they are strongly attracted by external magnetic field. Those are called ferromagnetic substances. For example, iron, cobalt, nickel, chromium dioxide. These are ferromagnetic substances. Why in these cases they attracted more towards magnetic field? Why? See, here these are domains. Domains means these substances contains unpaired electrons. When these unpaired electrons are grouping together, these substances contains unpaired electrons. When these unpaired electrons are grouping together, those are called domains. Those are called domains. So in that substances, all these domains are in same direction. Same direction means upward direction. Whenever these domains are in same direction in a given substance, automatically that substance is strongly attracted towards magnetic field. See, the substances in which domains are arranged in parallel direction, the net magnetic moment will be high. That is the reason behind that one. Next, ferromagnetic substances. What is this ferromagnetic? The substances in which the domains, I told you what are domains. The domains are arranged in parallel and anti-parallel direction. See, some domains are in parallel, some are in anti-parallel direction. With unequal number. See, here parallel direction 1, 2, 3, 4. Here anti-parallel direction 1, 2, 3. Automatically, its attraction, its magnetic moment will be less compared to ferromagnetic substances. What are the examples for this one? Fe3O4, Cu, Fe2O4, Mg, Fe2O4. These are the examples for ferromagnetic substances. What is ferromagnetic substances? The substances in which domains are arranged in parallel and anti-parallel direction. In anti-ferromagnetic substances, the substances in which the domains are arranged in parallel and anti-parallel direction with equal number. See, parallel 3, anti-parallel 3. Whenever these are in equal number, that means parallel and anti-parallel are in equal number, these domains are in equal number, that magnetic moment will be 0, because that one direction will be cancelled by other direction. Automatically magnetic moment will be 0. For that, examples are nickel oxide NiO, MnO2, V2O3. So these are the definitions, simple definitions. In case of ferromagnetic substances, all magnetic domains are arranged in one direction. Here magnetic domains are arranged parallel and anti-parallel in unequal number. Here parallel and anti-parallel domains are arranged in parallel and anti-parallel in equal number. Whenever they are in equal number, magnetic moment will be 0. Whenever they are in unequal number, the magnetic moment will be less. Whenever they are in same direction, whether in parallel or anti-parallel, then magnetic moment will be high. Here you should remember these examples. Examples are very important. This is all about magnetic properties of solids. This is all about solid state chapter. Thank you.